Your goals for learning. Let's begin by looking at the short-term regulation of rising blood pressure. In response to rising blood pressure, arterial walls are stretched, stimulating baroreceptors in the carotid sinus, aortic arch, and other large arteries of the neck and thorax. As a result, these receptors send off a faster stream of impulses to the brain.
Hello. I want to emphasize that the baroreceptors are most important for short-term regulation of blood pressure. This is amply proven by the fact that people do develop high blood pressure or hypertension. The baroreceptors in these people are still operating normally, but their set point for response is set higher when the short-term adjustments fail to bring their blood pressure down. Mostly, baroreceptors are important for restoring blood pressure when we make position changes. For example, when we stand up after sitting down. Okay, I'll see you.
In response to increased stimulation from the baroreceptors, the brain increases parasympathetic activity and decreases sympathetic activity. This leads to a reduction in heart rate, an increase in the diameter of the arteries, and therefore lower blood pressure, bringing blood pressure back down to normal levels. The next two screens illustrate the reduction in heart rate and increase in arterial diameter. Let's look at the effect of increased parasympathetic activity on the heart and blood pressure. With increased activity of the vagus nerve, which is part of the parasympathetic nervous system, and decreased activity of the sympathetic cardiac nerve, heart rate is reduced. This leads to lower cardiac output and therefore lower blood pressure. Click on the brain to see the efferent nerve impulses. Watch the effect on heart rate and blood pressure. Now let's look at the effect of decreased sympathetic activity on arteries and blood pressure. Vasomotor fibers are sympathetic nerves that innervate the smooth muscle of blood vessels. With decreased activity of vasomotor fibers, the vascular smooth muscle relaxes, arterial diameter increases, and blood pressure is reduced. Click on the nerve to see reduced vasomotor fiber activity. Watch the effect on the diameter of the artery and blood pressure. Let's recap the short-term regulation of rising blood pressure. Click on the carotid sinus or aortic arch to begin the process. In response to rising blood pressure, baroreceptors stretch, increasing impulses to the brain. This leads to increased parasympathetic activity and decreased sympathetic activity, resulting in slowing of the heart rate, an increase in the diameter of arteries, and consequently a reduction in blood pressure. Now let's look at the short-term regulation of falling blood pressure. When blood pressure drops suddenly, the baroreceptors are inhibited and they send fewer impulses to the brain. As a result, parasympathetic activity decreases and sympathetic activity increases, leading to an increase in blood pressure via three mechanisms. 1. Increased sympathetic impulses to the heart increase heart rate and contractility. 2. Increased impulses to the blood vessels increase vasoconstriction. And 3. Increased sympathetic impulses to the adrenal gland stimulate the release of epinephrine and norepinephrine into the bloodstream. These hormones enhance heart rate, contractility, and vasoconstriction. Together, these three mechanisms bring blood pressure back up to normal levels, as illustrated on the following screens. First, let's look at the effect of increased sympathetic activity on the heart and blood pressure. Increased sympathetic impulses to the heart and decreased vagus nerve activity lead to increased heart rate and enhanced contractility, increasing stroke volume. These changes result in higher cardiac output, which increases blood pressure. Click on the carotid sinus or aortic arch to begin the response to declining blood pressure. Watch the effect on heart rate and blood pressure. How does greater sympathetic activity affect arteries and blood pressure? Increased vasomotor fiber activity leads to constriction of vascular smooth muscle. The smaller arterial diameters give rise to increased blood pressure. Click on the nerve to see increased sympathetic activity. Watch the effect on arterial diameter and blood pressure. Now let's explore the effect of increased sympathetic activity on the adrenal gland and blood pressure. Increased sympathetic impulses to the adrenal gland stimulate the release of epinephrine and norepinephrine into the bloodstream. These hormones increase heart rate, contractility of the heart, and vasoconstriction of blood vessels, thus increasing blood pressure. Because they are carried in the blood, these hormones act more slowly than nervous system controls, and their effects are more prolonged. Click on the carotid sinus or aortic arch to begin the response to falling blood pressure. Watch the effect on the adrenal gland, the heart, and blood pressure. Here's a recap of short-term regulation of falling blood pressure. Click on the carotid sinus or aortic arch to begin the process. As blood pressure falls, baroreceptors are inhibited, resulting in decreased impulses to the brain. Parasympathetic activity is decreased and sympathetic activity is increased. Leading to increased heart rate and contractility, increased vasoconstriction, and the release of epinephrine and norepinephrine from the adrenal gland. All of these mechanisms contribute to raising blood pressure back up to normal levels. We will now explore the long-term regulation of low blood pressure. Long-term regulation is primarily accomplished by Here, we will simulate the loss of blood and demonstrate the chain of events which will restore blood volume and normal blood pressure. Click on the blood collection bag. Juxtaglomerular cells in the kidney monitor alterations in blood pressure. If blood pressure falls and remains low, these specialized cells release the enzyme renin into the bloodstream. Click on a kidney to start the process. The renin-angiotensin mechanism consists of a series of steps aimed at increasing blood volume and blood pressure. Step 1 is catalyzing the formation of angiotensin 1. As renin travels through the bloodstream, it binds to an inactive plasma protein, angiotensinogen, activating it into angiotensin 1. Click on the renin molecule. Step 2 involves converting angiotensin 1 to angiotensin 2. As angiotensin 1 passes through the lung capillaries, an enzyme in the lungs converts angiotensin 1 to angiotensin 2. Click in the box below. In the third step, angiotensin 2 stimulates aldosterone release. Angiotensin 2 continues through the bloodstream until it reaches the adrenal gland. Click in the white box to see a close-up view of the. Here it stimulates the cells of the adrenal cortex to release the hormone aldosterone. A secondary effect is that the angiotensin 2 is a vasoconstrictor and therefore raises blood pressure in the body's arterioles. The aldosterone mechanism is an important component of long-term blood pressure regulation. The target organ for aldosterone is the kidney. Here, aldosterone promotes increased reabsorption of sodium from the kidney tubules. Click in the black box to see a close-up view. The distal convoluted tubule winds through the kidney and eventually empties its contents into a urine-collecting duct. The peritubular capillaries absorb solutes and water from the tubules. Aldosterone stimulates the cells of the distal convoluted tubule to increase the active transport of sodium ions out of the tubule into the interstitial fluid. Click in the peritubular capillary to demonstrate the effect of aldosterone. As sodium moves into the bloodstream, water follows. The reabsorbed water increases the blood volume and therefore blood pressure. Click in the dehydration. As sodium moves into the bloodstream, water follows. The reabsorbed water increases the blood volume and therefore blood pressure. Click in the distal convoluted tubule to show the movement of water. Dehydration due to sweating, diarrhea, or excessive urine flow will cause an increase in osmolarity and a decrease in blood volume and blood pressure. As increased osmolarity is detected, there is both a short-term effect and a long-term effect. For the long-term effect, the hypothalamus sends a signal to the posterior pituitary to release antidiuretic hormone, abbreviated ADH. ADH increases the reabsorption of water in the kidney. ADH promotes the reabsorption of water from the kidney by stimulating an increase in the number of water channels in the distal convoluted tubules and collecting tubules. Click on the ADH molecule to see what it does. These channels aid in the movement of water back into the capillaries, decreasing the osmolarity of the blood and increasing the blood volume and therefore blood pressure. A short-term effect of increased osmolarity is the excitation of the thirst center in the hypothalamus. There are many other chemicals which influence blood flow and blood pressure. Most of them act by altering blood vessel diameter. Here's a summary of what we've covered. In the short term, rising blood pressure stimulates increased parasympathetic activity, which leads to reduced heart rate, vasodilation, and lower blood pressure. Falling blood pressure stimulates increased sympathetic activity, which leads to increased heart rate, contractility, vasoconstriction, and blood pressure. Long-term blood pressure regulation involves renal regulation of blood volume via the renin-angiotensin mechanism and aldosterone mechanism. Increased blood osmolarity stimulates release of ADH, which promotes reabsorption of water and excites the thirst center, resulting in increased blood volume and blood pressure. To see the related chapter out, your goals for learning. Autoregulation is the process by which the various organs and tissues of the body. Within each house, the residents can regulate the amount of water entering the house. Similarly, as long as mean arterial pressure is normal, the various organs and tissues of the body can regulate the amount of blood that enters them according to their needs at any given time. Blood flow regulation occurs at the capillary beds. The feeder arteriole brings blood to the capillary bed. The shunt is a short vessel that directly connects the feeder arteriole and the drainage venule at the opposite end of the bed. Exchanges of materials take place between tissue cells and the blood in the true capillaries. The precapillary sphincter is a cuff of smooth muscle fibers that surround the root of each true capillary, acting as a valve to regulate the flow of blood into the true capillaries. Click on each box to see what happens when precapillary sphincters are open or closed. The buildup of certain chemical signals locally acts as a metabolic control that causes the feeder arteriole to dilate, bringing more blood into the local area. These chemical signals also cause the precapillary sphincters to relax. For the following screens, click on the box showing the condition in tissue cells that you think will cause the precapillary sphincters to open in most tissues.
Nice to see you again. As you can see, when the precapillary sphincters are open and the true capillaries are flushed with blood, materials like oxygen, glucose, and other nutrients and waste are moving between the blood and the tissue cells. This is what circulation is all about, folks. It's to make sure that the cells get needed materials and can get rid of their wastes. Ta-ta!
Local physical factors acting on the vascular smooth muscle, such as changing blood volume and blood pressure, also act as autoregulatory stimuli. Click on each box to see the effect of changing blood pressure and blood volume on the local capillary bed. We will now look at how materials are exchanged between the capillaries and tissue cells. The true capillaries are the sites of solute exchanges between the blood in the lumen of the capillaries and the tissue cells. Several structural characteristics of capillaries aid the transport process. Capillary endothelial cells have fenestrations, which are pores that may be open or covered by a very delicate membrane, allowing for passage of fluids and small solutes. Clefts between cells also allow movement of materials between the blood and tissue cells. Cytoplasmic vesicles move materials across the capillary wall by bulk transport. Most solutes move across the capillary wall by diffusion, which is the movement of solutes from an area of higher concentration to an area of lower concentration. Lipid-soluble molecules, such as oxygen and carbon dioxide, diffuse through the lipid phase of the intervening plasma membranes. Click on an oxygen or carbon dioxide molecule to see these gases moving across. Some molecules which are not lipid-soluble are translocated by cytoplasmic vesicles in a process called exocytosis. Click on a yellow molecule to see exocytosis take place. Water-soluble solutes, such as amino acids and sugars, diffuse from the capillary through fluid-filled clefts or fenestrations. Click on a blue molecule to see how water. We will now explore fluid flows at capillary beds. Bulk fluid flows, which have little to do with nutrient and gas exchanges, also occur at capillary beds. Note the fluid leaving the capillaries at the arterial end and returning to the capillaries at the venual end. Bulk fluid flows are important in determining the relative amount of fluid in the blood and in the tissue spaces. Interstitial fluid, including any plasma proteins that have escaped from the bloodstream, enters the lymph capillaries. These leaked fluids and plasma proteins are carried back to the bloodstream by the lymphatic system. As the amount of fluid in the tissue spaces varies, the distance that solutes must travel between the blood and tissue cells changes proportionately. If there is more fluid in the tissue spaces, solutes must travel farther between the blood and tissue cells. Fluid flows represent the balance between hydrostatic and osmotic pressures acting at capillary beds. Let's look at just hydrostatic pressure first. Hydrostatic pressure is the pressure exerted by a fluid on the walls of its container. In capillaries, hydrostatic pressure is exerted by blood. Thus, capillary hydrostatic pressure is equivalent to the blood pressure in the capillaries. Capillary hydrostatic pressure is also called filtration pressure because it forces fluid out of the capillaries. Because of friction encountered in the capillaries, the capillary hydrostatic pressure is lower at the venual end of the capillary bed than the arterial end. In theory, the hydrostatic pressure of the interstitial fluid in the tissue spaces opposes the hydrostatic pressure in the capillaries. Normally, however, there is very little fluid in the tissue spaces because it is quickly picked up by the lymphatic capillaries, so the hydrostatic pressure of the interstitial fluid is very low. Net hydrostatic pressure equals the hydrostatic pressure in the capillary minus the hydrostatic pressure in the interstitial fluid. The net hydrostatic pressure forces fluid out of the capillary. Let's determine the net hydrostatic pressure at the arterial end of the capillary bed. Taking the capillary hydrostatic pressure of 35 millimeters of mercury minus the interstitial fluid hydrostatic pressure of 1 millimeter of mercury gives us 34 millimeters of mercury for the net hydrostatic pressure at the arterial end of the capillary bed. Now let's determine the net hydrostatic pressure at the venial end of the capillary bed. Here, 15 millimeters of mercury minus 1 millimeter of mercury gives us 14 millimeters of mercury for the net hydrostatic pressure at the venial end of the capillary bed. Now let's look at osmotic pressure. Osmotic pressure is the pull on water exerted by large non-diffusible solutes like proteins. The higher the solute concentration, the more the solution pulls or holds water. For each beaker shown, note the relative concentrations of solutes in the sac and in the bathing solutions. Then click on each beaker to observe the net movement of water in that system. The movement of a solvent, such as water, through a membrane from a dilute solution to a more concentrated solution is called osmosis. Because of its high content of plasma proteins, capillary blood has a relatively high osmotic pressure which tends to draw fluid into the capillary like the first sac on the previous page. Interstitial fluid contains few proteins because leaked proteins, like leaked fluids, are quickly gathered up by the lymph capillaries. Hence, interstitial fluid osmotic pressure is very low, 3 millimeters of mercury in this example. Net osmotic pressure pulls fluid into the capillary. Net osmotic pressure equals the osmotic pressure in the capillary minus the osmotic pressure in the interstitial fluid. In this typical capillary, the capillary osmotic pressure of 25 millimeters of mercury minus the interstitial fluid osmotic pressure of 3 millimeters of mercury results in a net osmotic pressure of 22 millimeters of mercury. Both net hydrostatic pressure and net osmotic pressure affect fluid flows at the capillary beds. Remember that hydrostatic pressure forces fluid out of the capillary blood and osmotic pressure pulls fluid into the capillary. If net hydrostatic pressure is higher than net osmotic pressure, fluid leaves the capillary. If net hydrostatic pressure is lower than net osmotic pressure, fluid enters the capillary. The net force, which determines the direction of fluid flow, equals the net hydrostatic pressure minus the net osmotic pressure. At the arterial end, will fluid leave or enter the capillary? Remember that the net force, which determines the direction of flow, equals net hydrostatic pressure minus net osmotic pressure. The net force at the arterial end of the capillary equals 34 millimeters of mercury minus 22 millimeters of mercury, which equals 12 millimeters of mercury. Since the net hydrostatic pressure is greater than the net osmotic pressure at the arterial end of the capillary, the hydrostatic pressure wins out and fluid leaves the capillary at the arterial end. At the venial end, will fluid leave or enter the capillary? The venous net force in the capillary equals 14 millimeters of mercury minus 22 millimeters of mercury, which gives us negative 8 millimeters of mercury. Since the net osmotic pressure is greater than the net hydrostatic pressure at the venial end, the osmotic pressure wins out and fluid enters the capillary at the venial end of the bed. Here's a summary of what we've covered. Local chemical and physical factors regulate blood flow to individual tissue cells. Lipid-soluble substances move through capillary walls by diffusion, whereas non-lipid-soluble substances are transported via pores or exocytosis. Clefts and fenestrations facilitate the process. The fluid flows occurring at capillary beds reflect the balance between hydrostatic and osmotic pressures acting inside and outside the capillary. To see the related